torque. Okay, how do we change the motion of an object? Well, what we learned in translational motion in the fall was we apply a net force. So that's a net force that's not zero, so it's unbalanced in one direction or another, and that will cause an acceleration in that same direction. Okay, so how do we make something rotate if it's not already rotating? In class, I used the example of a door because that's something we make move pretty much every day. But here, let's look at a bike tire. So if you want to set it going, all right, and you want to use your hand, you're going to pull with force F, all right, and you're going to want to pull tangential to the circle. You're not actually going to want to push in the same direction because that's not going to make it rotate. And that will cause you some rotation, some angular acceleration to occur. Now, if I have the wheel and I apply the force there, that's going to be the most effective. If I apply the force really close to the axle, I'm not going to get as much rotation out of my efforts. So we can tell that the more force I apply, the more something will rotate. And the farther away from the axis of rotation, the more I will cause it to angularly accelerate. All right, so let's put that in an equation form. We call this quantity torque. And we write it as actually the cross product of the distance from the center of rotation, so r for radius, as we've been using in circular motion, cross the force applied. What that really means is we don't have to do anything with matrices, vectors, craziness in this class, okay? All it means is that we're looking for the bit of the force that is perpendicular to the distance from the center of rotation, from that point of rotation. So we can write this, and this is how it is on your equation sheet, as tau equals RF sine theta, where theta is the angle between the force applied and if it's a door, between the door, if it's a bike, between the point of contact and the center of the rotation. The SI units for torque are Newton meters. Now, you might hear this as non-SI units as foot-pounds. So you see the Chevy commercials that talk about how many foot-pounds of torque the engine has. Foot-pounds is also a measure of torque. It's not SI units, though. And here's a huge caveat, okay? Newton meters, you might remember that if you take a force times a distance, you get work, which is measured in joules. This unit is from a cross product, not a dot product. Remember that force had to be in the same direction as your displacement, okay? So this is not equal to a joule. The units for torque must be Newton meters. So how do we make something accelerate? Well, in translational motion, your acceleration is proportional to your net force and inversely proportional to your mass. You'll remember this is our version of Newton's second law. In rotational motion, your angular acceleration is equal to your net torque divided by your moment of inertia. So your angular acceleration is proportional to your net torque and inversely proportional to how much that object wants to resist a change in its rotational motion. This is the rotational version of Newton's second law. We'll work on calculating net torque in a later lesson, but I want you to see this and understand the relationship and the analogy. Okay, some problem-solving strategies for rotational dynamics, which is what we're moving into. These should look very similar, okay, and you'll need these when we start working problems in class on Thursday. All right, so if you start out by examining the problem, you see that torque is going to be involved, something's rotating. Draw a sketch, okay? Make sure you know your system, just like we did when we were doing forces, and draw a free body diagram. You're going to do forces, and then if a force is perpendicular to the radial arm of the rotation, you're going to end up with a torque, okay? But we might have to deal with forces as well. So, label everything. Here are the key things. The sketch is just like we did before. So is the free body diagram. Okay, so your setup is going to be just the same as it was last semester. After that, you're going to apply the rotational version of Newton's second law. Okay, make sure you use the correct moment of inertia, and the torque is always about the point of rotation, okay? So you'll have to be careful with where that's defined. You'll have to note that in your free body diagram. Okay, and the last thing that's a little hidden there is check for reasonableness, all right, at the end. We will practice this in class on Thursday.